create the first weight here. So let's wait until the end of the epoch and see if the weight is actually created. Before actually finishing the training of the model, let's do another thing. We also would like to visualize the output of the model while we are training, and this is called validation. So we want to check how our model is evolving while it is getting trained. So what we want to build is a validation loop which will allow us to evaluate the model, which also means that we want to inference from this model and check some sample sentences and see if how they get translated. So let's start building the validation loop. The first thing we do is we build a new method called run validation. And this method will accept some parameters that we will use. For now, I just write all of them, and later I explain how they will be used. Okay, the first thing we do to run the validation is we put our model into evaluation mode. So we do model.eval, and this means that this tells PyTorch that we are going to evaluate our model. And then what we will do, we will inference two sentences and see what is the output of the model. So with torch.notgrad, we are disabling the gradient calculation for this for every tensor that we will run inside this with block. And this is exactly what we want. We just want to inference from the model. We don't want to train it during this loop. So let's get a batch from the validation dataset. Because we want to inference only two, so we keep a count of how many we have already processed. And we get the input from this current batch. I want to remind you that for the validation DS, we only have a batch size of 1. This is the encoder input, and we can also get the encoder mask. Let's just verify that the size of the batch is actually 1. And now let's go to the interesting part. So as you remember, when we calculate when we want to inference the model, we need to calculate the encoder output only once and reuse it for every token that the model will output from the decoder. So let's create another function that will run the greedy decoding on our model, and we will see that it will run the encoder only once. So let's call this function greedy decode. Okay, let's create some tokens that we will need. So the SOS token, which is the start of sentence. We can get it from either tokenizer, doesn't matter if it's the target or the source, they both have it. EOS, okay. And then what we do is we pre-compute the encoder output and reuse it for every token we get from the decoder. So we just give the source and the source mask, which is the encoder input and the encoder mask. We can also call it encoder input and encoder mask. Then we get okay, how do we do the inferencing? The first thing we do is we give to the decoder the start of sentence token, so that the decoder will output the first token of the sentence, of the translated sentence. Then at every iteration, just like we saw in my slides, at every iteration we add the previous token to the decoder input, and so that the decoder can output the next token. Then we take the next token, we put it again in front of the input to the decoder, and we get the successive token. So let's build the decoder input for the first iteration, which is only the start of sentence token. We fill this one with the start of sentence token. And it has the same type as the encoder input. Okay, now we will keep asking the decoder to output the next token until we reach either the end of sentence token or the max len we have defined here. So we can do a while true, and then our first stopping condition is if the decoder output, which becomes the input of the next step, becomes larger than max len, or reaches max len. Here, why do we have two dimensions? One is for the batch and one is for the tokens of the decoder input. Now we also need to create a mask for this. We can use our function causal mask to say that we don't want the input to watch future words. And we don't need the other mask because here we don't have any padding token, as you can see. Now we calculate the output. We reuse the output of the encoder for every iteration of the loop. We reuse the source mask, so the input, the mask of the encoder. Then we give the decoder input and along with its mask, the decoder mask. And then we get the next token. So we get the probabilities of the next token using the projection layer. But we only want the projection of the last token. So the next token after the last we have given to the encoder. Now we can use the max. So we get the token with the maximum probability. This is the greedy search. And then we get this word and we append it back to this one, because it will become the input of the next iteration. And we concat. So we take the decoder input and we append the next token. So we create another tensor for that. Should be correct. Okay, if the next token, so if the next word or token is equal to the end of sentence token, then we also stop the loop. And this is our greedy search. Now we can just return the output. So the output is basically the decoder input, because every time we are appending the next token to it. And we remove the batch dimension, so we squeeze it. And that's our greedy decoding. Now we can use it here in this function, so in the validation function. So we can finally get the model output is equal to greedy decode, in which we give him all the parameters. And then we want to compare this model output with what we expected, so with the label. So let's append all of these. So what we give to the input we gave to the model, what the model outputted, the output of the model, so the predicted, and what we expected as output. We save all of this in these lists, and then at the end of the loop we will print them on the console. To get the text of the output of the model, we need to use the tokenizer again to convert the tokens back into text. And we use, of course, the target tokenizer, because this is the target language. Okay, and now we save them, all of these, into their respective lists. And we can also print it on the console. Why are we using this function called print message, and why not just use the print of the Python? Because we are using here in the main loop, in the training loop, we are using here TQDM, which is our really nice looking progress bar, but it is not suggested to print directly on the console when this progress bar is running. So to print on the console, there is one method called print, provided by TQDM, and we will give this method to this function so that the output does not interfere with the progress bar printing. Okay, we print some bars. and then we print all the messages. And if we have already processed number of examples, then we just break. So why we have created these lists? Actually, we can also send all of this to TensorBoard. So we can, for example, if we have TensorBoard enabled, we can send all of this to the TensorBoard. And to do that, actually, we need another library that allow us to calculate some metrics. I think we can skip this part, but if you are really interested, in the code I published on GitHub, you will find that I use this library called the torch metrics that allows to calculate the char error rate and the blue metric, which is really useful for translation tasks, and the word error rate. So if you're really interested, you can find the code on the GitHub, but for our demonstration, I think it's not necessary. So, and actually this, we can also remove it, given that we are not doing this part. Okay, so now that we have our run validation method, we can just call it. Okay. What I usually do is I run the validation at every few steps. But because we want to see it as soon as possible, what we will do is we will first run it at every iteration, and we also put this model.train inside of this loop, so that every time after we run the validation, the model is back into its training mode. So now we can just run validation, and we give it all the parameters that it needs to run the validation. So give it model. Okay, for printing message, are we printing any message? We are, so let's create a lambda, and we just do and this is the message to write with the TQDM. Then we need to give the global step and the writer, which we will not use, but okay. Now I think we can run the training again and see if the validation works. All right, looks like it is working. So the model is okay, it's running the validation at every step, which is not desirable at all. But at least we know that the greedy search is working, and it's not, at least looks like it is working. And the model is not predicting anything useful. Actually, it's just predicting a bunch of commas because it's not trained at all. But if we train the model, after a while, we should see that after a few epochs, the model should become better and better and better. So let's stop this training and let's put this one back to where it belongs. So at the end of every epoch here, and this one we can keep it here, no problem. Yeah. Okay, I will now skip fast forward to a model that has been pre-trained. I pre-trained it for a few hours, so that we can inference it and we can visualize the attention. I have copied the pre-trained weights that I pre-calculated, and I also created this notebook reusing the functions that we have defined before in the train file. The code is very simple. Actually, I just copy and pasted the code from the train file. I just load the model and run the validation, the same method that we just wrote. And then I ran the validation on the pre-trained. Let's run it again, for example. And as you can see, the model is inferencing 10 examples, sentences, and the result is not bad. I mean, we can see that Levin smile, Levin sorrise, it's matching, and most of them matching. Actually, we could also say that it's nearly overfit for this particular data. But this is the power of the transformer. I didn't train it for many days. I just trained it for a few hours, if I remember correctly, and the results are really, really good. And now let's make the notebook that we will use to visualize the attention of this pre-trained model. Given the file that we built before, so train.py, you can also train your own model choosing the language of your choice, which I highly recommend that you change the language and try to see how the model is performing and try to diagnose why the model is performing bad. If it's performing bad or if it's performing well, try to understand how can you improve it further. So let's try to visualize the attention. So let's create a new notebook. Let's call it, let's say, attention visualization. Okay, so the first thing we do, we import all the libraries we will need. I will also be using this library called Altair. It's a visualization library for charts. It's nothing related to deep learning, actually. It's just a visualization function, and in particular the visualization function, actually I found it online. It's not written by me. Just like most of the visualization functions you can find easily on the internet if you want to build a chart or if you want to build a histogram, etc. So I am using this library mostly because I copied the code from the internet to visualize it, but all the rest is my own code. So let's import it. Okay, let's import all of this. And of course, you will have to install this particular library when you run the code on your computer. Let's also define the device. You can just copy the code from here. And then we load the model, which we can copy from here, like this. Okay, let's paste it here, and this one becomes vocabulary source and vocabulary target. Okay, now let's make a function to load the batch. I will convert the batch into tokens now using the tokenizer. And of course, for the decoder, we use the target vocabulary. So the target tokenizer. So let's just infer using our greedy decode algorithm. So we provide the model. We return all this information. Okay, now I will build the necessary functions to visualize the attention. I will copy some functions from another file because actually what we are going to build is nothing interesting from a learning point of view with regards to the deep learning. It's mostly functions to visualize the data. So I will copy it because it's quite long to write, and the salient part I will explain, of course. And this is the function. Okay, what does this function do? Basically, we have the attention that we will get from the encoder. How to get the attention from the encoder? For example, the attention we have in 3 positions. The first is in the encoder, the second one is in the decoder at the beginning of the decoder, so the self attention of the decoder, and then we have the cross attention between the encoder and the decoder. So we can visualize 3 types of attention. How to get the information about the attention? Well, we load our model, we have the encoder, we choose which layer we want to get the attention from, and then from each layer we can get the self attention block and then its attention scores. Where does this variable come from? If you remember, when we defined the attention calculation here, when we calculate the attention, we not only return the output to the next layer, we also give this attention scores, which is the output of the softmax. And we save it here in this variable self.attention scores. Now we can just retrieve it and visualize it. So this function will, based on which attention we want to get from which layer and from which head, will select the matrix, the correct matrix. This function builds a data frame to visualize the information, so the tokens and the score extracted from this matrix here. So this matrix, we extract the row and the column, and then we also build the chart. The chart is built with Altair, and what we will build actually is we will get the attention for all the I built this method to get the attention for all the heads and all the layers that we pass to this function as input. So let me run this cell now. Okay, let's create a new cell and then let's just run it. Okay, first we want to visualize the sentence that we are dealing with. So the batch other input tokens. So we load a batch and then we visualize what is the source and the target. then also the target. And finally we calculate also the length. What is the length? Okay, it's basically all the characters that come before the padding character, so the first occurrence of the padding character, because this is the batch taken from the dataset, which is already the tensor built for training, so they already include the padding. In our case, we just want to retrieve the number of actual characters in our sentence. So this one we can, the number of actual words in our sentence, so we can check the number of words that come before padding. So let's run this one. And there is some problem. Here I forgot to, this function was wrong, so now it should work. Okay, this sentence is too small, let's get a longer one. Okay, let me check the quality. You cannot remain as you are, especially you. Noi non possiamo, voi non potete continuare a stare così, specialmente ora. Okay, looks not bad. Okay, let's print the attention for the layers, let's say 0, 1, and 2, because we have 6 of them. If you remember, the parameter is n is equal to 6, so we will just visualize 3 layers, and we will visualize all the heads. We have 8 of them for each layer, so the head number 0, 1, 2, 3, 4, 5, 6, 7, and 7. Okay, let's first visualize the encoder self attention, and we do get all attention maps, which one we want, so the encoder one, and we want these layers and these heads, and what are the row tokens, the encoder input tokens, and what are the what do we want in the column, because we are gonna build a grid. So as you know, the attention is a grid that correlates rows with columns. In our case, we are talking about the self-attention of the encoder, so it's the same sentence that is attending itself. So we need to provide the input sentence of the encoder on both the rows and the columns. And what is the maximum number of length that we want to visualize? Okay, let's say we want to visualize no more than 20, so the minimum of 20 and sentence length. Okay, this is our visualization. We can see, and as we expected actually, when we visualize the attention, we expect the values along the diagonals to be high, because it's the dot product of each token with itself. And we can see also that there are other interesting relationships. For example, we say that the start of sentence token and the end of sentence token, at least for the head 0 and the layer 0, they are not related to other words, like I would expect actually. And but other heads, they do learn some very small mapping. We can, if we hover over each of the grid cells, we can see the actual value of the self-attention, so the score of the self-attention. For example, we can see the attention is very strong here, so the word especially and specially are related, so it's the same word with itself, but also especially and now. And we can visualize this kind of attention for all the layers. So because each head will watch different aspect of each word, because we are distributing the word embedding among the heads equally, so each head will see a different part of the embedding of the word. We also hope that they learn different kind of mapping between the words, and this is actually the case. And between one layer and the next, we also have different WQ, WK, and WV metrics, so they should also learn different relationships. Now we may also want to visualize the attention of the decoder, so let's do it. Let me just copy the code and just change the parameters. Okay, here we want the decoder one, we want the same layers, etc. But the tokens that we will be on the rows and the columns are the decoder tokens. So decoder input tokens and decoder input tokens. Let's visualize. And also we should see Italian language now because we are using the decoder self-attention. And it is. So here we see a different kind of attention on the decoder side. And also here we have multiple heads that should learn different mapping, and also different layers should learn different mappings between words. The one I find most interesting is the cross attention. So let's have a look at that. Okay, let me just copy the code and run it again. Okay, so if you remember the method, it's encoder, decoder, same layer. So here on the rows we will show the encoder input, and on the columns we will show the decoder input tokens, because it's a cross attention between the encoder and the decoder. Okay, this is how the more or less how the interaction between the encoder and the decoder works and how it happens. So this is where we find the cross attention calculated using the keys and the values coming from the encoder, while the query is coming from the decoder. So this is actually where the translation task happens, and so this is how the model learns to relate these two sentences to each other to actually calculate the translation. So I invite you guys to run the code by yourself. So the first suggestion I give you is to write the code along with me with the video. You can pause the video, you can write the code by yourself. Okay, let me give you some practical examples. For example, when I'm writing the model code, I suggest you watch me write the code for one particular layer, and then stop the video, write it by yourself, take some time, don't watch the solution right away, try to figure out what is going wrong. And if you really cannot, after 1-2 minutes, you cannot really figure out what is the problem, you can have a glimpse at the video. But try to do it by yourself. Some things, of course, you cannot come up by yourself. So, for example, for the positional encoding and all this calculation, it's basically just an application of formulas. But the point is, you should at least be able to come with a structure by yourself. So how all the layers are interacting with each other. This is my first recommendation. And while about the training loop, the training part actually is quite standard. So it's very similar to other training loops that you may have seen. The interesting part is how we calculate the loss and how we use the transformer model. And the last thing that is really important is how we inference the model, which is in this greedy decode. So thank you everyone for watching the video and for staying with me for so long. I can assure you that it was worth it, and I hope in the next videos to make more examples of transformers and other models that I am familiar with and I also want to explore with you guys. So let me know if there is something that you don't understand or you want me to explain better. I will also for sure follow the comment section, and please write me. Thank you, and have a nice day.